component.
Thank you very much. And many thanks to Professor Be for inviting me and creating such a lively atmosphere. What I want to talk about is a joint work with Joe Rabinow. And at the beginning, it will not have connection to function fields per se, but in fact, later on, it's kind of connected to a question that arises in a work of Geckler and Reversat from mid-90s. So let me just first of all tell you what these notions are that appear in the title. And my notation will be the following. K will be a local field. R will be a ring of integers. And small k will be the residue field. And then E, an elliptic curve, is an optimal quotient of X, and this is a smooth projective curve. If there is a morphism from X to E which does not factor through a non-trivial isogeny, so this does not exist. So this is essentially equivalent to saying that equivalently the induced map from the Jacobian of X to E has connected and the reduced kernel. And also equivalently, which is sometimes convenient, there is a, so this is the Albanese map. And then by Picard, you also have a map in the reverse direction. So the condition that it's optimal, it means that E actually embeds into the Jacobian. So this is by Picard, induced from that map. All right, and then what is a Mumford curve? X has degenerate reduction over R. Well, let's not specify. Just let's say there's degenerate reduction, or is a Mumford curve. If there is a semi-stable model X of X over R such that this closed fiber is a bunch of P1, is a union of projective lines intersecting transversely. In double points. So you can imagine it could be the closed fiber could be something like this. So, and all these lines are P1s. So Mumford proved a famous theorem that curve X has a kind of a analytic uniformization in this setting, exactly when it has this type of reduction. All right, now, and the last thing I want to say is to define these component groups. So I have three notions. Sorry, I have to define this one too. So the component group, if your A, so if X is Mumford, then J, by which I will denote the Jacobian of X, has degenerate reduction, which means that if you consider the neuron model, then this is the connected component is a torus of the closed fiber, and then the component group, the connected component of the identity is a torus, and then the component group is a abelian group, which is the quotient of the closed fiber of the neuron model by its connected component of identity. So the point is that this is not necessarily connected, and there is a group that measures how far it is from being connected. All right, so I pretty much defined everything I want, and now I can state the main question that I was trying to understand with Rabinov. And the question is due to Ribet and Takahashi. A question. So the question is the following. Suppose this pi is optimal. Is the induced map from the component group of the Jacobian to the component group of E optimal, and X is Mumford? Is this map necessarily surjective? Okay, so before giving you the answer, let me give some motivation why anybody would care about this. There are some famous arithmetic curves which are Mumford, and you probably know that one of those is x0p. So example, if you take x to be x0p over qp, then probably everybody here has seen this picture that the reduction at p of this curve consists of two projective lines intersecting like this. So this is a Mumford curve in this sense, and then you can prove, so theorem This is due to Mestre I think the accent is on one of the E's, the second one. And then there is a more general result due to Matt Emerton. So the theorem says that this is surjective. So let me sketch a quick proof to give you some sense of what kind of number theory is involved in this type of questions. So suppose you have such an optimal quotient and you want to prove that the component group, the map on component groups is surjective. It is in fact enough to consider the dual picture. I have to show the dual There is some theory, non-trivial theory involved in this, developed by Grothendieck, which you can use to show that if this is injective, then this map will be surjective. So, and for this, this is more convenient. So suppose you want to prove this. Okay, then suppose this is not trivial for some prime L. Okay, now because it's a quotient of x, you can show, or it's an easy implication of the theory of neuron models, that E has multiplicative reduction. If it's a quotient of Jacobian with this type of reduction, totally degenerate, then suppose that this is not 1, then it means that EL extends to a finite flat group scheme. Over ZP. Okay, or what is usually said is that this is finite. So people studying representations arising from this type of group schemes say that this representation is finite. Now, if EL is irreducible as Galois module, then you get a contradiction by a theorem of Ribet, famous level lowering. So you see, if it is irreducible, and since it is finite, and because by modularity it arises from a modular form of level P, Ribet tells you that you can actually strip off this level. So E would arise from a Cus form of level 1, which is a contradiction. Then get a contradiction. By Ribet's level lowering. Now, if it is reducible, on the other hand, if EL is reducible, then you can, it's not hard to show that this contains, then it contains either a constant, contains either this group scheme, so it has actually a rational point, or it contains mu L. Or in other words, the Cartier dual of this will be a constant group scheme. Now, so what does this imply? Well, the implication is because E sits inside of the Jacobian, in either case, it implies that the intersection of EL is non-trivial, either with the torsion subgroup, rational torsion subgroup of J, or the Shimura subgroup. Okay, so then EL intersects either JQ torsion or maximal mu type subgroup. And now a famous theorem of Maser tells you what these are. So this is the cuspidal divisor group. So this is cuspidal divisor group. And Maser proved that this is the Shimura subgroup. Okay, so now what's the contradiction? Well, contradiction is that Maser also showed that both groups map non-trivially into the component group. So if you chase this diagram, you get that this map, the EL, cannot map trivially into this group, which is a contradiction. Okay, so the point is there is some very non-trivial number series used here, namely Ribit's level lowering and some of the deepest results in Maser's Eisenstein ideal paper.
So the problem was local from the beginning, but how did you extend to the global setting?
Well, if E is a optimal quotient over QP, then it's actually defined over Q.
Oh, I see.
Yeah. All right, now here's a second example. And I'll put it in quotation marks to be commented later on. So now consider the Shimura curve xd 0m. So where d is indefinite quaternion algebra over Q ramified at primes dividing this D, and this D is a product of even number of primes. Okay, then for any, consider X to be this curve over QP where P divides D. Then it's known by theorem of Cherednik and Drinfeld X is a Mumford curve. Okay, it has this type of reduction that I mentioned. And then a theorem of Takahashi says that in this case pi is also surjective. So in fact, when we were trying to answer this question of Ribet and Takahashi, well, once you have these two theorems, the motivation is the following. Is it just a general geometric fact that if you have this type of curve, curves, then this map on component groups is always surjective, or there is always some non-trivial number theory that happens in the background that forces this fact. Okay, so that was the motivation. And the expectation was that this is somehow a general fact because this proof didn't really use much besides the fact that these are Mumford curves. And there are other reasons that you would expect this to be surjective. Matt Baker told me about this question, so he was trying to prove it. Now, when we were trying to answer this question, we started looking at this proof, and unfortunately, it has a gap. So this is not an example, but it's not completely clear if the answer is yes or no here. So it remains a very interesting open problem that I want to pose, that in case of Shimura curves, it would be very interesting to know if you can actually give a positive answer. And so the general answer to the question of Ribet and Takashi is no. So I will just give you a construction which shows why this is so. And the construction is based on well-known type of constructions that go back to maybe Legendre even. All right, so here's the construction. So you take, first assume that the residue field is not F2. If it is F2, then it is surjective for stupid reasons. I will explain later. But, and now fix n dividing this number. Okay, and fix two Tate curves which are not isogynous over K bar, but have component groups isomorphic to Z mod n Z. Okay, so well, what this essentially means that you take the periods Q1 and Q2 so that ORD Q1 is ORD Q2 is n, but Q1U is not Q2W. So you can easily choose such elements. And now, under these assumptions, you get that EI, so these two curves, E1 and E2, you get that the n torsion is K rational. So non-canonically you can split it like this. Okay, so now there is a canonical subgroup of EIN corresponding to okay, so what I mean by this, E has multiplicative reduction, and if you consider the connected component of the identity of the neuron model, this is a torus. So this is GM, and its n torsion contains this. Okay, it's one-dimensional. So then you can lift that uniquely to En, and you get a canonical subgroup, and you fix a generator. Fix a generator GI of this subgroup, and a generator Z of Mihran. Okay, then you have this wave pairing. Okay, so wave pairing. Now it's known that this is alternating. So you can choose, we can find, so this is alternating. So we can find HI such that EIN is the direct sum of these two groups, and EN G1 H1 equal EN G2 H2 is equal to this Z. Okay, so you sort of choose appropriate bases of En with certain restrictions on the wave pairing of these elements. And now we can describe the construction, the actual thing. All right, so yeah. So we have you can define a unique isomorphism of groups, which is defined in terms of generators like this. So you switch the generators, right? So this is an anti-isometry. Meaning that En phi p phi q is En p q inverse. All right, now here's the construction. You take A to be E1 cross E2, and you take a subgroup of the n torsion of AN is the graph of this isomorphism. Right, so you take the graph, and now you take the quotient, and that's the counterexample, and I will explain why. All right, so here's a theorem So first, this is a Jacobian. And second, the component group of this is trivial. So the first one is kind of classical. People were studying this type of quotients for a long time, and if you choose sort of this subgroup appropriately, the quotient will not split. So you get a Jacobian. Where it is important for choosing this map in this funny way is forcing this to happen. But this is also not difficult to check. All right, so where is the contradiction? Well, the contradiction is in the construction itself. It's clear that EI actually embeds into J, is optimal. But these curves, by construction, have large component groups, and the Jacobian has a trivial component group. So obviously, you cannot have a surjection. All right, and if you want a very explicit equation-based example, you can unwind what's going on and in some cases write down the equation of this curve that gives you the Jacobian. In fact, this is a genus 2 curve, so you can in some cases find its equation. So if you take these two Legendre curves, okay, over QP, P odd, and you take X to be this hyperelliptic curve, then there is a series of Igusa which is similar to Tate's series. You can compute some numbers called Igusa invariant and determine what is the structure of this. So this X, the reduction is just the minimal regular model is a projective line intersecting in 2 points. And this is X FP. And again, from this Igusa invariance, this is a work of King Liu. You can show that this is 1. So, well, it's sort of, you know this by the theorem, but you can check it directly from the equations. And then to show that these are optimal for this curve, you can write down a map. A morphism is given by this. So you can check that this is a degree 2 map. Right? Well, since it's of degree 2, it's obviously optimal. And the Legendre curves, by just computing a J invariant, has component group Z mod 2Z. Right, so you don't need the theorem, you can just use equations if you want. Now, in the remaining 10 minutes, I want to say more about the theory. So this shows that somehow there is there should be some non-trivial number theory happening for this question to have a positive answer, because in fact there is abundance of these counterexamples. And this comes back to the work of Gekel and Reversat that I mentioned. So because J is a Jacobian of a Mumford curve. It has a rigid analytic uniformization. I will not I will not state the theorem that gives you analytic uniformization. I'll just write down the sequence, and if you know what this means, then many of you have seen this, of course. So by CK star, I'm denoting the multiplicative group of the completion of the algebraic closure of K. And so there is a lattice. This is a torus, and there is a lattice that gives you the CK points of J. And this map is given by a certain pairing. So and here the map is lambda going to lambda. And this is a bilinear, so this is bilinear, symmetric, and order of this is positive definite. All right? So then, if you have an optimal quotient, or you have an elliptic curve with split multiplicative reduction, it also has a uniformization. So let me write it here. This is by Tate. Okay, and we know that there is this map. So sorry for doing this, but since I'm running out of time, I'll just be messy and write the diagram this way. So there is this map, and the question is how this uniformization is related to this one. Now, in case of Drinfeld Jacobians, Gekel and Reverset have this beautiful result, which tells you that the thing that you need to do is essentially to evaluate this pairing at the point at the vector corresponding to E. So what's going on here? J E induces this map. So you can choose. Let's see. What do I want to denote this? This is like the dual. So we take 1 to be the generator of gamma. This is, of course, Z. This is isomorphic to Z. This is C lambda E, and this is a primitive element. Okay? All right. So let me state this theorem now, and I will explain the proof on this diagram, which I will not erase. So, first of all, the endomorphism ring of the Jacobian is naturally a subring of this lambda. Then you have an idempotent element, E. This is from J to J. So this is idempotent to E. And then let me define these two quantities. So if I denote this ord by this symbol, then you take the minimum and you take this to be the orthogonal complement and denote n the degree of this map. Okay, so here's the theorem that we prove using this uniformization, is that the following are equivalent. Pi star phi j to phi e is surjective. Two, this C is 1. 3, this E is primitive in the endomorphism ring of lambda. 4, M is the order of this QE, and 5, N is lambda So let me say what this is. You can think of this this quantity as the congruence number of E in this lattice. So this is like the congruence number, and this is the degree. All right, so the motivation for doing this comes from this work of Geckler and Reversad, where in case of Drinfeld Jacobians, they essentially, well, Geckler then in a separate paper, sort of discusses cases where you can prove this for Drinfeld Jacobians. So, what is the meaning of C then from this perspective? It kind of has the same flavor in some sense as the Manin constant. So these gamma and lambda are the homology groups in this setting, and you have a map between them. So this surjectivity of these component groups is related to the map on the homology being saturated, okay, which is similar to the Manin constant. Now, what's the construction? We essentially show that, let me erase this now, that you can get this uniformization from J by evaluation map. So you map lambda to lambda E. All right, and you show that then you get this lattice maps to kind of C gamma. So it doesn't map exactly to gamma, it maps to something larger. There could be a torsion subgroup here, and this torsion is really that C. Now, in Geckler-Reversad, this is done for Drinfeld modular Jacobians, and the proof relies on Heck operators. So the main observation that we make here, and we show that it works, that you don't really need the Heck algebra to carry this out. So you just need this idempotent, and you need it to behave in a certain way with respect to this pairing, and this you can prove by from rigid analytic theory, and that is enough actually. So all right, I have 5 minutes. Okay, good. Now let me come back to Takahashi's thing and say where is the mistake. So the mistake is not really in Takahashi's paper per se, but it's in a paper of Bertolini and Darmon. And if you assume this result of Bertolini and Darmon, then you easily get C2B1. So here's a remark. Let me maybe find the correct reference. Well, so this is Bertolini and Darmon. This is in Duke 1999, I think. It's something like a p-adic. Let's see. So it's called p-adic periods, p-adic L functions, and the p-adic uniformization of Shimura curves. So they have a proposition there. If you read the proposition, in the proof, what they really do, implicitly they just assume that this is true. Okay, for the case of Shimura curves. Now, for their purposes, this is still fine. The main formula there will be just multiplied by this constant that comes out. But if you care just about the constant itself, they make an implicit assumption, and so we communicated this to Darmon and Bertolini, and they agreed that it's incomplete. So in case of Shimura curves, sort of remains an interesting question what's going on, but the existing proof is false. All right, and let me just finish with a remark on so second remark is that this theorem, which is sort of a generalization of a theorem of Gekeler, you can use this theorem along with a pairing that Gekeler constructs in case of Drinfeld modular Jacobian. So he constructs a pairing based on interpreting this as the space of automorphic forms. So these are the harmonic cochains Z-valued. So using the Fourier expansion, you can construct such a pairing, which is the analog of the well-known pairing where you take a modular form and a Heck operator and map it to the first coefficient. So it proves that this is perfect. You can use this to show that E is primitive in that case, which implies that C is 1. So for J0n, where this n is some ideal, and you consider this over the completion of your function field, this is FQ1 over T. Well, this is still a degenerate Jacobian, so it follows that this is surjective. So this Ribet-Takahashi question has a positive answer for Drinfeld Jacobians, and there is again a number theoretic reason. Namely, you can interpret this lattice as a space of automorphic form, and there is a non-trivial fact that's happening, that there is a pairing like this. There is a large algebra that lives in the endomorphism ring of the Jacobian. Okay, so for a different number theoretic reason, again you get this to be true. Well, we're trying to figure out if something like this also works for Shimura Jacobians, but so far we are not successful. Well, we can prove it in some very special cases, but the general case seems to be much more complicated, and it's related to these level lowering results of Ribet. So you need them in much larger generality than is known, and it's not clear if such theorems are true or not. Just a final remark, if you're curious how this translates, this construction, to the original example, I can tell you what the lattice is of this two-dimensional Jacobian that we constructed. So let me just put it here. The example, so construction rigid analytically. So here's the lattice. You take lambda, and suppose you fix two generators. And now you have to define a pairing into K, which satisfies these properties. It's symmetric, and the evaluation is positive definite. So here's what you do. You define E1 to be Q1, E2 to be Q2, and you define E1, E2 to be E2, E1 to be the Z, which was the root of unity. And then you take the lattice, take J to be, it doesn't write anymore, to be C, K star, two copies. So this two-dimensional torus modulo lattice generated by Q1 Z and ZQ2. So you can show that you get a abelian variety, and this is really the analytic incarnation of that algebraic construction that I gave at the beginning. Okay, so, and then you can check that the theorem is correct. In fact, if you consider the evaluation at lambda 1, what you get this mu c cross Q1z. So you, under this evaluation, you do get torsion groups. And this is a question that arises in Jekyll-Röverset construction. So it is not clear if their construction always gives you trivial mu c. So by this result, it's true in this case. But in general, it's not clear if it's true or not. And there should be arithmetic reasons, not geometric, because geometrically it's false. All right, so I'll stop here.